All right. So this is our first meeting for UTMIST's reading group 2021. So I guess start with an introduction about me. My name is Yvonne. I'm in computer engineering. I'm an undergrad in third year. My pronouns are V and them. I'm just kidding though, don't sue me. And my interests mainly are in algorithms and reinforcement learning right now. So over the summer, I was doing research with Professor Gennady Pakimenko, and we worked on accelerating reinforcement learning workloads with like GPUs and kernel fusion. So yeah, and this is my favorite meme in machine learning. Prior knowledge of statistics, probability theory, calculus, and linear algebra is strongly recommended. Oh no, anyway, import numpy as NP, import torch. So, I mean, it's funny, but at the same time, it's like, it really shows there's some problems right now in the field of machine learning. There's a lot of hype about it, which is nice, and there's people trying to get in. But I think at the same time, you do need those math at some point in time, right? And you do need a good foundation. So I guess that leads to what this reading group is for. So I guess my motivation for creating this group is so that people can actually look at academic papers, learn the actual theory behind how things work, and not be so intimidated by it and actually enjoy the theory aspect of things. So this is our first year running this. So I do want a lot of feedback from you guys. And how this is gonna work is it's essentially a guided reading group. So I'm going to be doing some talking. I'm going to present like my take on the papers, but if we can, and if you guys have time to read the papers, I'd also like to see some discussion about like the ideas in the papers, so we can all bounce ideas off of each other. And yeah, like I said, please give me feedback. Let me know how you want this group to be run, so we can all benefit from it together. So how exactly do the logistics work? As mentioned before, it's very easy. At the start of each month, we choose a paper together, I'll announce it, and then you'll have 3 weeks to read it. And on the last Saturday of each month, we'll have a meeting and we'll talk about it, have a presentation about it. So basically, start of each month, you'll see a poster like this on our social media. Hopefully you saw this month. So here's some resources for the reading group. There's not much. Mainly the GitHub is just for, the presentation, the slides, and sometimes I have codes, maybe if I'm not too lazy. The Discord channel though, do join that because we're gonna be doing most of the discussion and like figuring out which paper to read next on Discord, hopefully. So yeah, that's a quick overview of how the paper reading group is gonna work. Any questions so far? No? No, we're all good? Okay. Cool. So really no questions? Is there any papers that you guys would like to read? Can I just get like an idea of what the experience of everybody is? Like, has everybody read papers before? You can do like a react on Zoom. I believe you can say like yes or no, or just give me a thumbs up if you have. Yeah? Okay. Nice. Nice. Yeah, I did see on the sign up sheet that most of us have read papers before. So that's pretty good. But if you haven't, don't be intimidated. It's the whole point of this is so that we can help you like read these more easily. So without further ado, this month's paper is deep residual learning for image recognition, aka the first paper where ResNets are introduced. You do see that it's sort of an old paper. It's from 2016, but I think it's still very worth exploring. And this will just give you an idea of how the reading group will go as well. So yeah, here we go. So I'm going to talk about first why I chose this paper, and then we'll get into actually seeing how this, like the dissection of the paper. I actually don't have any code for you today, unfortunately. I will do better next time, but because it's ResNets, there's been like so many reproductions already, and there's so many things built on it. So I have a few resources for you. You can still look into that. And then we'll talk about related works, because every time you read a paper, it's never just about reading this one paper, right? You want to survey the entire landscape sort of and see where this paper fits in. So then, yeah. So why did I choose this paper? Oh, and the PowerPoint is messed up. That's okay. Well, I guess, yeah, like ResNets are the state of the art in computer vision. And even though it's 2016, you'll see that most of the ideas after 2016 still build on top of ResNets. So really, this is like the most recent breakthrough in terms of how we actually think about the architectures. The paper is relatively easy to read, I think, compared to some more verbose papers. It's only 12 pages, so I hope some of you have time to already like glance through the paper. If not, that's okay too. Yeah, and applications of ResNets, they're actually everywhere. Like, so this is sort of like the statistics I got from papers with code, and it shows how compared to, hold on, let me just get a laser pointer. Can you guys see my mouse? Yeah, okay. All right, so yeah, so this one really shows how ResNets just suddenly blew up and got so many citations after AlexNet, VGG and stuff. And then other tasks, you have like all these different tasks from image classification to, you know, all kinds of like even not computer vision tasks. I think I've seen them. Sorry, do you mind removing? Oh, I'm so sorry. Yeah, I will remove the blue text as Hayte pointed out. Okay. Pardon me? Are you saying something, Jason? Jason? Okay. Sorry, I think you were just unmuted for a second. Yeah, no worries. Yeah, okay. So I was saying before, there's so many applications of ResNets. And I don't know if you guys went to Tesla's AI Day, but in it, they were presenting their state-of-the-art perception networks for their autopilot. And what they used was actually a variant of ResNets. So obviously ResNets, they won the ImageNet challenge. And they also did really well on CFR10. So this is like classification problem for millions and millions of images. And then the last application is kind of interesting because I just heard this from one of our academic mentors. And he was saying that they use ResNets to monitor the deforestation of a region of land over time. So it's interesting to see that ResNet is also able to handle like time series data. So ResNet's really powerful, they're everywhere. Yeah, and now this is the paper. Sort of, these are the first 3 pages, and I crossed out related work because, you know, you want to do that on your own. You sometimes they try to give you like misleading information. They try to talk down the papers that are related. You should glance over it because it does give you ideas of what are related, but you should always do your own related work research. So that's my suggestion on that. And basically, so from those 3 pages, you can already have like an idea of what this paper is about. And essentially it's saying that, okay, here you have like 2 weight layers with a value in the middle, and say these 2 layers together are trying to learn a function f of x. Then what a residual network does is it actually adds the skip connection, as we call it, from x to, let's say the output is y. So then now your y is composed of f of x and the identity function x. And I guess we'll see as we read the paper why this is helpful, but some intuitions already are that you sort of retain knowledge as you go through the layers. So that you don't lose any information and you never do worse than the previous layer, because obviously the solution space of f of x plus x contains x, right? So, and their motivation in the paper was that when you have deeper neural networks in 2016, right? Sometimes they see, or actually almost always, they see a degradation in performance, whereas our intuition for neural networks is always that if you have deeper nets, then you should be able to represent more and more complex functions. So this was pretty baffling, and they were trying to solve this problem. And their proposal was that this skip connections that they add and trying to learn this residual function, f of x plus x. So it's called residual because you have like this residual term from the previous layer, which is x, right? And so their proposal is this actually solves the degradation problem. And the results were that, yeah, actually they can build deeper nets and they're more accurate. And yeah, using this method, they're able to won the ImageNet challenge, as well as do super well other classification benchmarks. So some more benefits of this include that compared to previous methods, they don't have any extra parameters that are introduced, no more memory and no more complexity as well. So basically, their idea is that if you have deeper nets and you have residual layers, then you have better accuracy. And we'll see if this is true, you know. So at this point, you can already like formulate a bunch of questions that should be answered as you read the paper. For me, always is, did their result actually support their core idea? Were their results strong enough? You know, was there integrity in their results? And then some more paper-related questions were what actually causes accuracy degradation? Why is it easier to optimize the residual mapping than the original f of x? So we'll see if those are answered. Page 4 is just sort of this big figure showing how the residual network is done. So you can see all these like skip connections along the way. So that's not too interesting, but here from 5 to 8, the pages 5 to 8, you can actually see their experimental results, and this is where things get interesting. So my question 1 was, did their results support their core idea? In other words, were deeper resonance more accurate than their plane counterparts? And this is true. So this graph is showing on the left, it's showing the plane networks, so without the skip connections. And I believe the bold curves are validation errors, and slightly less bold ones are the training errors. So these are training curves. And on the right, you can see that for ResNets, the 34-layer ResNet is actually getting better accuracy than the 18-layer. But this is not true for planets. The 34-layer one actually does worse. So obviously they have made some kind of breakthrough here. And you can also see in their summary table that their results, the accuracy was much higher. Now, hold on to your papers, because now they report that an ensemble of ResNets actually got 3.57% error on the ImageNet challenge. And I think this was never done before, and this was a huge thing. Now, the second question was, what causes degradation? So why is it that as we add layers, we get worse accuracy? And what they said was, well, like there's like a big misconception that the degradation is caused solely by vanishing gradients or exploding gradients. And if you don't know, exploding gradients are like this problem where when you're propagating your gradients through the layers, because, well, without loss of generality, you can think of them as linear layers that multiply by a weight each time. So if you have a big discrepancy between the weights, then your gradient gets bigger and bigger and bigger until it's like exponentially big. So that makes it really hard for your optimizers to find a good solution. But in this paper, they actually argue that it's not caused by vanishing gradients because they've done batch norm on the plane networks and they're still bad. So what they conjecture is that it's actually caused by exponentially low convergence rates. So it converges much, much later when you have a deeper neural network. This is unsupported in their paper, and I really like to see maybe more future works building on top of this. Yeah. So there's also an interesting result from this paper that ResNet layer responses have a small standard deviation. And by layer responses, they just mean the weights in each layer. So that means maybe in layer 1, you have weights with a mean of 5, and I'm just making things up though. And their standard deviation is pretty small. But you don't see that in plane networks. So for plane networks, they have a standard deviation. So here you have like the yellow ones are the plane networks, and that standard deviation is much higher, right, in general than the ResNet counterparts. So this is, and this is a figure that is just the sorted version of the one on the left. So this is pretty enlightening because when you have a smaller standard deviation among the weights, you can show that this discourages the vanishing or exploding gradients problem, even though that's not, what they were really trying to solve. And they also say that when there are more layers, any individual layer of ResNet tends to modify the signal less. So I guess I found this part a little surprising because they seem to claim that the residual functions themselves are closer to 0, even though they're showing the standard deviation, right? So that doesn't really tell you what the actual values are. I thought that was kind of suspicious, but if that was true, that residual functions are closer to 0, that means so residual functions are f of x plus x, right? And that's supposed to represent your underlying function. So then your f of x, which is what your layer is actually learning now, if it's close to 0, that means your x is much close. So that means the underlying function is very close to the identity mapping. So like all of these things we're doing in deep learning, at the end, it's just trying to learn something that's really close to the identity mapping, which I found is pretty interesting. So are our questions answers? Did the results support their core idea? I think so. It's definitely a very strong paper. And I think it stood the test of time, as we know. So Number two, what causes accuracy degradation? And their idea is that it's not vanishing or exploding gradients problem. It's actually that deeper nets take exponentially more time to converge. My third question, why is it easier to optimize the residual mappings? I guess they did claim that the weights are closer to zero, but there was no evidence really in the paper. So I guess that's also future works. So after I dissect the paper, I think mainly, well, generally I want to show you like a code demonstration of it and verify if the results were actually right. But today I don't have time to prepare all that, so I'll just give you a bunch of resources instead. This Medium tutorial is actually pretty good. I think it goes like tells you step by step how to code up a ResNet. And the slides will be uploaded on GitHub right after the meeting. Yeah, so then related works. So we all know this guy, Schmidt-Huber, right? Who the godfather of everything that has ever been invented in AI. And this Twitter post of his, he was actually saying that ResNets were copying their idea of highway networks. And this is kind of true, actually, because highway networks were cited in the original ResNet paper. So it was interesting to see that the authors of the ResNet paper, they actually did like a comparison study of ResNets and highway networks. And basically highway networks, they're sort of like the more complex versions of residual mappings. So remember how we have f of x plus x, but like y is a summation? We could have had like, I don't know, a XOR gate, AND gate, anything, right? And that's actually the idea of highway networks. And highway networks, because they have more complex gates for shortcuts, they actually allow the network to sometimes learn the residual mapping and sometimes not. So your network has a choice of between using the values from the previous layer or not. And I guess so then it's kind of surprising that the results were that much in favor of ResNets than highway networks, since highway networks should really contain ResNets. But I guess it's the idea of like, you should focus on one thing and just get very good at it instead of trying to incorporate as much information as you can into the network. So I encourage you to read this paper. It's very interesting. This will also be in the, ooh, it's messed up. Yeah, so anyways, that paper will be in the links and resources page, the last page of the slideshow. So then there's some more ResNet variants. For example, there's ResNet ABC. AB were actually proposed in the ResNet paper. Basically, they're saying, well, what if you're having a skip connection? As you know, in CNNs, we shrink the layers often, and that means your dimensions won't agree for f of x and x. So how do you sum it up? And one way you can do that is you introduce a new parameter which shrinks x, but I guess the trade-off is that you have more complexity in your network and more parameters to tune. So then so ResNet is from Microsoft research in 2016. Then in 2017, 1 year later, Facebook AI, they released ResNext, which I think, so it's basically like an ensemble of ResNets. What they do is they split out into a bunch of different networks, and then they combine it with addition at the end, and still include a shortcut layer. So it's a lot like Inception, and the like I guess the idea behind Inception is sort of you split and then transform and you merge together again. And the most recent variant for ResNet, and this is actually used in the Tesla perception networks. This is called RegNets, and they're basically residual networks that are regulated with RNNs. And that's pretty interesting, actually, because the whole idea of recurrent networks is that they have this like feed forward mechanism. And you see that in ResNets too, which is why they handle time series data just like RNNs. They have some sort of like memory built into them. Um, and in most recent developments, you actually see a combination of all of these networks. So convolutional networks plus recurrent neural networks. They're doing pretty well. They're used everywhere. So thirdly, some questions I still have is why is it easier to optimize the residual mapping? And are the weights actually closer to zero? Yeah, so that's like a quick dissection of the paper. Do you guys have any questions so far? Any suggestions for the next paper?